Hello and welcome to the third session on moment distribution method and myself Vahini M of GEC Haveri. Let us continue with the analysis of continuous beam without sinking. Let us consider a continuous beam ABCD with one of the ends as fixed and the other ends as simple supports. Okay, so the extreme support D is also a simple support. In the last case we have taken both ends of a fixed beam as fixed. Both ends of a continuous beam as fixed. In this case we will replace the one of the ends as simply supported end. So let us check what is the variation or what the changes we have to do to analyze a continuous beam with one of the ends as simply supported end. Okay, so that we can draw SFD, BMD and elastic curve. So as usual, the first step is to find the fixed end moments. So MFAB, since it is subjected to an eccentric point load, so the distance between the point load and the left support is 3 meter and the point load and the right support is 2 meter. So this is an eccentric point load. So to calculate MFAB, so the equation to be used is minus WAB square by L square, where minus W is the load magnitude, A is distance of the load from left end 3 meter, B is distance of the load from the right end 2 meter and L is span of the beam. So if we substitute those values, it becomes 40 into 3 into 2 square by 5 square and it will be minus 19.2 kilonewton meter. Next, MFBA is calculated by using WBA square by L square. Again the same values you have to substitute here. W is 40, B is 2 meter and A is 3 meter, 3 square by 5 square. So that will be 28.8 kilonewton meter. Next, BC is subjected to UDL throughout. Therefore, MFBC is calculated by using the relation minus WL square by 12, where W is intensity of the UDL and L is span of the member BC. So substitute the values minus 10 into 4 square by 12, WL square by 12. So that will be equal to minus 13.33 kilonewton meter. Similarly, MFCB is calculated by plus WL square by 12 and that will be equal to plus 13.33 kilonewton meter. And CD is also subjected to the same magnitude of UDL. So therefore, but only change is it has got a length of 5 meter. So MFCD is also calculated by minus WL square by 12, that will be equal to minus 10 into 5 square by 12, that will be equal to minus 20.83 kilonewton meter. And MFDC is calculated by plus WL square by 12 and that will be equal to plus 20.83 kilonewton meter. Next step is to calculate the distribution factors. So the distribution factors are calculated only for the intermediate joints. So in this case we have got two intermediate joints B and C. So under B we have got two members BA and BC and under C we have got two members CB and CD. So let us check how to find the distribution factors for these members. So the calculation is represented in the form of a table. So the first column is joint, next is members, next is relative stiffness and total stiffness, and then distribution factor, which is calculated by K, that is relative stiffness, divided by sigma K, that is total stiffness. So let us consider the first intermediate joint, that is B. The members meeting at joint B are BA and BC. So for BA, since the far end A is fixed, so the relative stiffness is calculated by I by L. So it is I by 5, that will be equal to 0.2 I. Next member meeting at joint B is member BC and the relative stiffness is also equal to I by L. So the length of the member is 4 meter, therefore I by 4. and the relative stiffness is 0.25I. So the total stiffness is summation of relative stiffnesses of the members meeting at a joint. So 0.2I plus 0.25I, that is equal to 0.45I. And the distribution factor is calculated by relative stiffness to total stiffness. So distribution factor for BA is equal to relative stiffness for BA divided by total stiffness. So 0.2I divided by 0.45I, that will be equal to 0.44. And distribution factor for BC will be equal to relative stiffness for BC divided by total stiffness, that is 0.25I divided by 0.45I, that will be equal to 0.56. So the next joint is joint C, and the members meeting at joint C are CB and CD. For CB, the relative stiffness is same, I by L, that will be equal to I by 4, and which will be equal to 0.25I. Next, the member is CD member. So we have replaced the fixity at joint D by a simple support. Therefore, the relative stiffness is calculated by using the relation 3/4 of I by L. So 3/4 of I divided by length is 5 meters. So if you substitute those values, it will be equal to 0.15I. So now the total stiffness is summation of relative stiffnesses of the members meeting at a joint. So 0.25I plus 0.15I, that will be equal to 0.4I. And the distribution factor for CB is relative stiffness of CB to total stiffness at C. So that is 0.25I to 0.4I, that will be equal to 0.625. And for CD member, it is relative stiffness, that is 0.15I divided by total stiffness, that is 0.4I, which will be equal to 0.375. So that is the calculation of distribution factors for member BA, BC, CB and CD. Next step is to distribute the moments, that is moment distribution. So again, the distribution is carried in the form of a table. In the first row, we will write the joints of the given beam. Okay. So the first joint is joint A, second one is B, third one is C, and the fourth one is D. So next, in second row, we will write the members coming under or meeting at each joint. So at joint A, we have got member AB. At joint B, we have member BA as well as member BC. And at C, CB and CD are the members meeting at C. And at D, member DC is meeting at D. So next, in the next row, we will write the distribution factors for each member. For AB, we don't have the distribution factor. For BA, it is 0.44. For BC, 0.56. For CB, 0.625. And for CD, it is 0.375. So that is the distribution factors. Next step is to write the fixed moments. So whatever we have calculated in the first step, those values have to be entered here. MFAB minus 19.2, MFBA plus 28.8, MFBC minus 13.33, MFCB plus 13.33, MFCD minus 20.83, and MFDC is plus 20.83. So till this point, everything will be same. Next is balancing. So when the both ends of a continuous beams are fixed, we will be balancing only the intermediate joints B and C. Whereas in this case, since joint D is a simply supported end, so we know that bending moment at a simply supported end is always equal to 0. So we will balance it, or we will make this moment as 0 first. So let us balance joint D first by applying how much? By applying minus 20.83. So to make the moment at D as 0, we have to apply a moment of minus 20.83 at joint D. Okay. As soon as we apply a moment at joint D, some portion of this moment will be carried to the far end. So the next step is carry over. So from DC to CD, it will be carried from DC to CD. So the far end for DC is CD. Okay. So half of this moment will be carried to CD. So half of 20.83 is minus 14.415. So now we have carried the moment from DC to CD. So next step is we will total the values at this stage so that we can make it as 0. So we will keep these values as it is because there are no values here. So AB 19.2, BA 28.8, BC minus 13.33, CB plus 13.33 and CD it is minus 20.83 minus 10.415, that will be equal to minus 31.245, and at D it is 0. So now we have balanced joint D. Okay, so in the next steps we should not look into this column D. Okay, only thing we have to balance joint B and joint C. So next steps are as usual, balancing and carryover, balancing and carryover. Only we have to balance joint B and joint C. So next we will balance joint B and joint C. So the imbalancing moment at joint B will be 28.8 minus 13.33. 28.8 minus 13.33, that will be equal to 15.47 plus. So 15.47 is the imbalancing moment at joint B. So to balance it we have to apply minus 15.47. So minus 15.47, that moment has to be distributed among the members meeting at joint B according to the distribution factors. So minus 15.47 into 0.44 will be equal to minus 6.807. Next, minus 15.47 into 0.56 will be equal to minus 8.663. So that is the balancing of joint B. Next, at C, 13.33 minus 31.245. So that is minus 17.915 is the imbalancing moment at joint C. So the imbalancing moment is minus 17.915. Therefore, the balancing moment will be plus 17.915. We have to apply a moment of plus 17.915 and distribute it according to the distribution factors. So 17.915 into 0.625 will be equal to 11.197. Next, 17.915 into 0.375 will be equal to 6.718. So now we have balanced joint C. Next, as soon as we apply different moments at B and C, some moments will be carried to the far end. So the next step is carry over. So the moments are carried from BA to AB. So the far end for BA is AB. So half of minus 6.875 will be equal to minus 3.403. So half of this will be carried to the far end AB. Next, from BC to CB, it will be carried from BC to CB. Half of minus 8.663 will be equal to minus 4.331 from BC to CB. Next, similarly from CB to BC. So the moment 11.197, half of this moment will be carried from CB to BC. So half of 11.197 will be equal to 5.598. So now we cannot transfer from CD to DC because we know that the carryover factor when the far end is hinged or simply supported, it will be 0. Therefore, it cannot take any moment. So you should not again carry the moments from CD to DC. We have already balanced it. So don't look into the last column, that is column D. Okay, so only we have to carry from BA to AB, BC to CB and from CB to BC. Next, again the step of balancing. So now again, as the moments are carried from CB to BC, joint B gets imbalanced. it is imbalanced by 5.598. Therefore, the balancing moment will be minus 5.598. So, minus 5.598 into 0.44 is minus 2.463, and minus 5.598 into 0.56 will be equal to minus 3.135. That is the balancing of joint B. Next, joint C is imbalanced by minus 4.331. Therefore, the balancing moment will be plus 4.331. So, 4.331 is distributed among the members according to the distribution factors. 4.331 into 0.625 will be equal to 2.706. Next, 4.331 into 0.375 will be equal to 1.625. That is the balancing. Next, again the step of carryover from BA to AB. Half of minus 2.463 will be equal to minus 1.231, and from BC to CB, half of minus 3.135 will be equal to minus 1.567, and from CB to BC, half of 2.706 will be equal to 1.353. So these are the carryover moments at BC, okay, and as well as A. So next is again balancing. So joint B is imbalanced by plus 1.353. Therefore, the balancing moment will be minus 1.353. Minus 1.353 is distributed according to the distribution factors. Minus 1.353 into 0.44 will be equal to minus 0.595, and minus 1.353 into 0.56 will be equal to minus 0.757. Next, joint C is imbalanced by minus 1.567. Therefore, balancing moment will be plus 1.567. So, 1.567 into 0.625 will be equal to 0.979, and 1.567 into 0.375 will be equal to 0.587. So, that is the balancing of joint B and C. Next step is carryover. Again, from BA to AB, half of minus 0.595 will be equal to minus 0.297, and from BC to CB, half of minus 0.757 will be equal to minus 0.378. Next, from CB to BC, half of 0.979 will be equal to 0.489. That is the carryover step. Okay. So, next we will continue. So, I have taken the last column, carryover moments. So, next step is to balance the joint B and joint C. Again, joint B is imbalanced by 0.489. Therefore, imbalancing moment is 0.489. So, balancing moment will be minus 0.489. So, minus 0.489 into 0.44 will be equal to minus 0.215, and minus 0.489 into 0.56 will be equal to minus 0.273. Next, joint C is imbalanced by minus 0.378. So, balancing moment will be plus 0.378. So, 0.378 into 0.625 will be equal to 0.236. and 0.378 into 0.375 will be equal to 0.141. So that is the balancing of joint B and C. Next, one more cycle we can go, that is carry over from BA to AB. Half of minus 0.215 will be equal to minus 0.107. Next, from BC to CB, half of minus 0.273 will be equal to minus 0.136. And from CB to BC, half of 0.236 will be equal to 0.118. That is the carryover step. Next is balancing. So, joint B is imbalanced by 0.118. Therefore, balancing moment will be minus 0.118. So, So minus 0.118 into 0.44 will be equal to minus 0.052. Next, minus 0.118 into 0.56 will be equal to minus 0.066. Next, joint C is imbalanced by minus 0.136. Therefore, balancing moment will be plus 0.136. So, 0.136 into 0.625 will be equal to 0.095, and 0.136 into 0.375 will be equal to 0.051. So, next, to get the final moments, you have to add all the values from total. You should not add it from fixed end moments, because we have already added the moments till this level. So therefore, don't go for adding the values from fixed end moment. You have to add all the values in each column from the total. Okay, so you have to add all the values from total. So that is under A, minus 19.2 plus minus 3.403 minus 1.231 minus 0.297, like that. Whereas under CD it is minus 31.245 plus 6.718 plus 1.624.587, like that. Okay, so you have to add all the values in each column from the row total. Okay, from the row of total you have to add all the values. Okay, so next, to get the final moments, so MAB is minus 24.24, MBA is plus 18.668, and MBC is minus 18.668. So now you can see the summation of these moments are 0. Okay, and MCB is 22.13, and MCD is minus 22.124, and MDC is 0, because it's a simple and it should be 0. We have already made it 0 in the first step of balancing. Okay, so these are the final moments. So using these moments, we will calculate the support reactions, plot SFD and BMD. So next step is to find the support reactions. So support reactions are calculated by considering each span individually along with the end moments. Okay, so let us consider AB span with the end moments. MAB minus 24.24, therefore anti-clockwise, and MBA plus 18.67, therefore it is clockwise. Okay, so AB is subjected to an eccentric point load. It is 3 meter from the left end and 2 meter from the right end. So let us apply the 3 equilibrium conditions. So since at A we have a fixed end, therefore HA does exist. So since there are no inclined or horizontal forces, when we apply sigma Fx is equal to 0, which implies HA as 0. Okay. Next, apply sigma Fy is equal to 0, which implies VA plus VB1 is equal to 40 kilonewton. Okay. Next, take sigma MA is equal to 0. So take summation of moments of all the forces about A and equate it to 0. So that is equal to minus VB1, because it is inducing anti-clockwise moment about A. So minus VB1 into 5. Next, plus 40. So this 40 is inducing clockwise moment about A. Therefore, plus 40 into 3. Next, this clockwise moment of 18.67 and this anti-clockwise moment of minus 24.24 is equal to 0. So if you calculate it, you are going to get the value of VB1 as 22.88 kilonewton. So using this value of VB1, substitute back into this VA plus VB1 is equal to 40. So VA value will be equal to 17.12 kilonewton. So that is the reactions for AB member. So next we will consider BC member. So BC member is subjected to UDL with the end moment. So at MBC it is minus 18.67, therefore anti-clockwise moment, and MCB is plus 22.13, therefore clockwise moment. Okay. So reactions at B and C are VB2 and VC1. So let us apply the equilibrium condition of sigma Fy is equal to 0. which implies VB2 plus VB1 minus, since it is subjected to UDL, to convert it into a point load, intensity into length, 10 into 4 is equal to 40 kilonewton. So VB2 plus VC1 is equal to 40 kilonewton. Next we will apply sigma MB is equal to 0, that is take moment of all the forces about B and equate it to 0, which implies minus VC1. So this is going to induce an anti-clockwise moment about B. So minus VC1 into 4. Next plus 10 into 4 into 2. So this converted point load, to convert this UDL into point load, this is going to act at the midspan. So 10 into 4 into, so the midspan length will be 2. So 10 into 4 into 2. Next this clockwise moment of 22.13 and this anti-clockwise moment of minus 18.67. So that is equal to 0. So if you work it out, the VC1 value will be 20.86 kilonewton. So therefore VB2 will be equal to 19.14 kilonewton. When you substitute the value of VC1 into this equation, you will get the value of VB2 as 19.14 kilonewton. So the reaction at B is the summation of VB1 plus VB2. So that is equal to 22.88 plus 19.14, that is equal to 42.02 kilonewton. So total reaction at B is 42.02 kilonewton. Next, let us consider the last member, that is CD member. So CD is also subjected to UDL of 10 kilonewton per meter. So this is the member CD along with the end moments. So at C we have a negative moment, that is minus 22.13. So since it is minus, we have represented it as in the anti-clockwise direction. So at D it is 0, therefore there are no moments at D. Okay. So the reactions at C and D are VC2 and RD. So let us apply the equilibrium condition. Sigma Fy is equal to 0, which implies VC2 plus RD is equal to 10 into 5, that is equal to 50 kilonewton. Next, take moment of all the forces about C and equate it to 0. So which implies minus RD into 5 plus 10 into 5 into 2.5, half of the 5 meters, and then minus 22.13, that is equal to 0. So that implies RD is equal to 20.57 kilonewton, and then VC2 will be equal to 29.43 kilonewton. So total reaction at C is the summation of VC1 and VC2, so which implies 20.86 plus 29.43 will be equal to 50.29 kilonewton. This is the total reaction at C. So these are the calculations of support reactions. So next we'll plot the shear force diagram. To draw the shear force diagram, consider the given beam along with the given loading and also the support reactions. So reaction at A is 17.12, at B it is 42.02, at C 50.29, and at D 20.57. So to draw the shear force diagram, consider a baseline of same length as that of the given beam. So positive shear forces are drawn above the baseline and negative shear force are drawn below the baseline. So the sign convention what we follow is, from the left to right, upward forces are taken as positive. So left of A 0, right of A we have an upward force of 17.12. So mark it above the baseline for 17.12 kilonewton. So next, right of A to the left of E. So since there are no loading, so shear force will be constant in between right of A to left of E. Next, just to the right of E, we have a downward force of 40 kilonewton. So therefore 17.12 minus 40 kilonewton will be equal to minus 22.88 kilonewton. So this ordinate should be equal to minus 22.88. Next, from right of E to left of B, there are no loading, so therefore shear force will be constant in between right of E to left of B. Next, shear force to the right of B, we have an upward force of 42.02, therefore minus 22.88 plus 42.02 will be equal to plus 19.14 kilonewton. Then from right of B to left of C, a UDL is acting throughout the length, so this magnitude has to be deducted from 19.14. So 19.14 minus 10 into 4, that will be equal to minus 20.86. Okay, so since it's a UDL, so this has to be a linearly varying line. Okay, so left of C it is minus 20.86, and just to the right of C we have an upward force of 50.29. So minus 20.86 plus 50.29 will be equal to plus 29.43 kilonewton. So this ordinate from the above the baseline, it should be 29.43 kilonewton. So shear force to the right of C is 29.43, and shear force to the left of C, a UDL is acting in between, so 29.43 minus 10 into 5 will be equal to minus 20.57. So left of D it is minus 20.57, and shear force to the right of D minus 20.57 plus 20.57 will be equal to 0. So the shear force always should join to the baseline. So this is the shear force diagram. So the values above the baseline are taken positive and the values below the baseline are taken negative. This is the shear force diagram. Next, we have to plot the bending moment and elastic curve. So to draw the bending moment diagram, consider the given beam along with the loading, and then consider the support moments so to draw the support moment diagram, consider the support moments as shown in the figure. So AB minus 24.24, BA plus 18.67, BC minus 18.67, CB plus 22.13, CD minus 22.13, and DC it is 0. Okay. So to draw the bending moment support moment diagram, use the thumb rules. So for the left end, left thumb, and for the right end, right thumb. So the direction of thumb will indicate the where we have to plot the ordinate of support moment diagram. So to draw the support moment diagram, draw the baseline as same length as that of the given beam. So we have at end AB, we have an anti-clockwise moment. So the direction of left thumb is indicating in the upward direction. So a line is marked in the upward direction for 24.24 kilonewton meter. Next at BA, a clockwise moment. So this is the right end for AB member. So use the right thumb. So the right thumb is moving in the upward direction. So mark it above the baseline for 18.67 kilonewton, and then join these two points with a straight line. So this magnitude is 18.67. Next we will consider BC member. So again BC, at B we have a anti-clockwise moment, left thumb. So left thumb is moving in the upward direction. So the same point can be considered. And for CB, this C is the right end. So the direction of right thumb, again it is moving in the upward direction. So for 22.13, so mark a line for 22.13 kilonewton meter. Then join these two points with the straight line. Okay, so this magnitude is 22.13. And for CD member, at end C, this is the left end. So left thumb, again the left thumb is moving in the upward direction. And at D, so since there are no moments, it is 0. So this itself is the magnitude of MDC. So join from 22.13 to 0. So this is the support moment diagram, over which we have to superimpose with the free bending moment diagram. So free bending moment diagrams are plotted by considering each span as a simply supported beam. So AB is a simply supported beam subjected to an eccentric point load. Therefore, the free bending moment diagram will be a triangle. So this highest ordinate will be always under the point load, whose magnitude is calculated by WAB by L, where W is magnitude of load, A is distance from left end, and B is distance from the right end, and L is the span. So if you substitute 40 into 3 into 2 divided by 5, it will be 48 kilonewton meter. Next, BC, it is subjected to UDL. Therefore, the variation of UDL will be a parabola, and the magnitude is calculated by using WL square by 8. So, which is equal to 10 into 4 square by 8, that will be equal to 20 kilonewton meter. Next, for CD member, it is also subjected to UDL. So, the variation of BMD is also a parabola. So, with the highest ordinate at the midspan, which is calculated as WL square by 8, and it is equal to 31.25 kilonewton meter. So, these are the support moments free bending moment diagrams. So, always the free bending moment diagrams are positive and support moment diagrams are negative. So, the points where these two overlap, those points are called as points of contraflexure. So, at these points the bending moments are 0. So, this is the portion of net positive bending moment, okay, and this is the net negative bending moment. So, supports are always subjected to negative bending moment, and midspans are always subjected to positive bending moment. So, this is the bending moment diagram. So, next, to draw the elastic curve, consider the given beam without loading. That means without loading, only with the end supports. Okay. So, the variation of elastic curve will be as that of the bending moment. So, since at A we have a fixed support, the displacement will be 0 for some region, and then because the sagging bending moment dominates, so the displacement or deflection will be in the downward direction. Okay, in this region the displacement will be in the downward direction, whereas at the support B, so negative bending moment occurs. So therefore a hogging bending moment takes place. The beam hogs in the upward direction, and then again in the mid portion for BC member, sagging bending moment dominates. So therefore the beam deflects in the downward direction, and at C hogging bending moment, and at D bending moment is 0. So therefore the deflected curve will just join at point D. Okay, you can observe at A, if you draw a tangent to the elastic curve, it will be in line with the beam. So there will be no slope at all. That means at a fixed support the slope is 0, whereas at a hinge or a roller or a simple support, you can draw a tangent to the elastic curve which makes a certain angle. So that angle is nothing but the slope. Okay, so therefore at fixed end the slopes should be 0, and at the simple end or hinge or a roller there should be some slope. Okay, so that is how you should draw the elastic curve. This is the elastic curve for the given beam. Okay, so this is how a continuous beam with a simple end can be solved. Okay, so the only change is to balance the simple supports first and then go on balancing the intermediate joints. That is for this session. Thank you.